All right, last session for this block. This panel is titled The Latest in Powder Bed Fusion. I'm excited to hear the thoughts from these speakers. The moderator is Dr. Mihaela Vlassi from the University of Waterloo. And at this time, we'll invite our speakers up. Hi, I'm Mihaela.
Hi, everyone.
All right, so we've got a
Hello.
Sarah. Yep.
Hello, everyone.
Hi. And then one more. There we go. Awesome. All right, ladies, I'll leave the floor to you.
All right, excellent. I hope everyone can hear and see us. Thank you so much, Amy. And really right on time, it is my pleasure to welcome you, our audience, as well as our accomplished speakers to our panel on the latest in powder bed fusion. My name is Mihaela Vlassi. I'm an assistant professor at the University of Waterloo and the co-director of the Multi-Scale Additive Manufacturing Lab, the largest academic metal AM lab in Canada. And I'm extremely enthusiastic to be the moderator for today's event and to host panelists with a really diverse background in metal AM, but really with a unique mission of addressing some of the technology leaps in materials, advanced characterization techniques, modeling and simulation, process optimization, and so on. And our accomplished panelists today will reveal how their industry and academic research work impacts the AM field, and also a little bit of their outlook on future directions in metal 3D printing. And we have three panelists. We have Sarah Wolf, assistant professor at Texas A&M, Dana Drake, lab engineer in metals at EOS North America, and Joy Gokul, associate professor at the Colorado School of Mines. And throughout the panel today, I highly encourage you to post your questions in the Q&A channel. And I think everyone can see it, and we'll do our best to address them. So I'll try to kind of prompt panelists as we go. So our first panelist, Sarah Wolf, is an assistant professor at Texas A&M University. Her research is really quite interesting as it focuses on in situ imaging of AM processes. And specifically, she uses X-ray and thermometry, which is really, really cool. The goal for today's, the goal of this research is really to identify and control the laser material interactions during the additive manufacturing process, to really provide new methods for either processing or synthesizing or building on new materials with tuned properties. And her areas of application span biomedical prosthesis, aerospace components, and various different structural components across different industry sectors. So, Sarah, can you maybe comment on your career path and how you got to where you are today, and describe one of the most interesting projects that you're presently working on?
Yeah, it's nice to be here, especially with some amazing women. So I actually studied environmental engineering as an undergrad, and during that time, I got to get a little work experience at an aerospace company, and I was working on like wastewater treatment, but at that time, I was and this was before metal AM became a big thing, but they were working on plastic prototyping, rapid prototyping, and just being exposed to the assembly and fabrication. I became really interested in manufacturing, so I switched majors for grad school to mechanical, and then since then I was kind of thrown into these laser metal interaction types of projects, including some additive manufacturing projects. And then it was a little serendipitous, but I went to school at Northwestern, and we're about an hour away from a synchrotron source, which is a high energy X-ray source at Argonne National Lab. So there was kind of a serendipitous visit, and that's where I was like, aha, this is what I really love to do now. I really want to use this high energy X-ray to take a look at the metal additive manufacturing process. So I've been working on that since then in many different capacities. And now I'm at Texas A&M as a pretty new professor. And I'm also trying to look at different types of materials as well. So in terms of really interesting projects, I just had a master's student who graduated, and she was really interested in the feasibility of printing lunar regolith materials. So we found a simulant, something that tried to simulate moon dust, and we just tried laying it on a bed of as powder and then try to print it, and it actually works out pretty well. It was very beginning stages of trying to print something like that, but yeah, just having that flexibility and kind of freedom to try was really cool.
Thank you so much, Sarah. I think we have lots of questions, at least on my end, on characterization techniques, and I'm really excited to have you on the panel. Our second panelist, Dana Drake, is the metals laboratory engineer for EOS North America, where she manages a metallurgical testing laboratory. And she works quite a bit on characterization of powder feedstock, as well as characterization of components, and collaborates quite a bit with applications and R&D engineers across EOS and other industry sectors. A bachelor's in metallurgical and materials engineering, and a master's in materials science from the Colorado School of Mines. And really her studies focused on industry testing standards, which are highly relevant, and their applicability to AM, where there's a high need, with an emphasis on powder properties. So her background is extremely relevant to the work that she's doing today at EOS. And again, Dana, I think your background is highly indicative of a lot of hands-on laboratory work and metallurgy. What are some of the most important skills that you draw upon daily from your academic background? And what are some of the really interesting projects that you're currently working on at the moment?
Yeah, well, thank you for me today. I'm excited to be on with these folks. It's exciting. Yeah, my experience in school and also laboratory, that I consider myself pretty lucky. I was trained as a metallurgist in school, and I get to use that every day. So it's pretty cool. A lot of friends of have nothing to do with what they end up doing for their careers, and so I consider myself lucky at some place where I do. There's so many aspects of it, and I've always been kind of a hands-on person, so the laboratory is pretty excellent. But I use stuff that I learned in my junior year metallurgy laboratory, like to prepare samples. I use that daily. In grad school, I learned all about the powder testing and all of the powder testing, just the diversity of how to test a powder, just because of there's the individual powder particles that have their own properties, and then when you put them all together, they behave in certain ways, and so that's another place to characterize. So a lot of my industry standards work that I did during grad school is actually pretty applicable to developing the testing methods that we're doing in my laboratory now, and trying to just make them better. And that goes hand in hand with like some of the processes that people want to characterize, or some of the features of powders. They don't have an industry standard yet. So industry standards take years to do, and even with a lot of the technical cooperation, which is like kind of unprecedented between the like international the ISO groups and the STM doing that together, that's pretty unprecedented with the work group that they started just for additive. So that's pretty cool, and they're kind of working together with the standards. But that comes into my life daily, and it's a lot of fun too, because I learned all that hands-on stuff, get to apply it, and then on occasion when I have students come in either as interns in other parts of the company, or I get to do a little bit of the teaching stuff, which is something that I always really appreciated. And, you know, thank you to all of my TAs that spent the 3-hour lab help me polish a sample. Your support has really made a difference in my life. So thank you for that. And some of the most interesting stuff that I'm working on is, you know, kind of, I have twofold. So I get to do solids parts analysis, and I also get to do powder analysis. So one of the things that not quite in my research project for the in research in the industry. So I kind of have a time frame for, like, a time of year where I do enter that. But one of the projects that I'll be working on in that time frame this year will be on powder and what happens when you store it for a while. What happens to the particle behavior? What happens to the chemistry? So I have ability in my laboratory to detect interstitial elements, oxygen, nitrogen, and hydrogen by inert gas fusion. So that's something that I'll be doing, as well as some of the more standard powder characterization techniques for performance. One of the things last year that was pretty interesting was I looked at the effect of what happens when your build pauses. So your build chamber's still closed and everything's still inerted, but something happens, the machine stops. At the last panel, they mentioned getting parts from Dallas during the freeze last year. So we had major power outage. So or something that affect or even just brownouts, just surges will affect looking at the different time scales of build pauses was something that was really interesting to me. And I did it short term, like 5 minutes, 2 hours, 24 hours. What was the effect on a fairly robust material? So Inconel 718, one of the first materials that became popular, and one that has a really robust parameter set. So all of the material stuff, and then looked at the microstructural and also the static mechanical properties of those samples. And so that was pretty interesting to me. Got to set up the machine myself, and being a lab person, being allowed with the additive machines was really exciting for me. As you know, people who are you know, they show me a new piece of equipment and I immediately want to know everything about it. So it was super exciting for me to be able to work with my, get a little glimpse into their world, and that's one of a couple of the things that have been interesting in my life recently.
And I think it's really exciting to see an overly excited material scientist, which is always a pleasure to have on the line. Lots of questions on the materials thread, Dana, and thank you so much for that overview. And our third panelist, Joy Gokul, is an associate professor in the Department of Mechanical Engineering at the Colorado School of Mines. And her research is really exciting. It spans several aspects of additive manufacturing, and she focuses on connecting the processing structure and properties, as well as performance relationships across the entire supply chain in the powder bed fusion process, using modeling, in situ monitoring, materials characterization, and mechanical testing. And really, this area of research is quite rich, and it provides a window into understanding the behavior of the fabricated components as they relate to process parameters. So Joy, welcome to the panel, and I'm really curious to know, what is the most exciting project that you're presently working on, and where do you think that may lead you?
Yeah, thank you for the introduction and having me on the panel today. Picking the most exciting project is always a hard thing, because one of the things I love about being a professor is I get to work on a lot of different things. So I think I'll pick one of my more recent projects, which has actually been because of my move to Mines. So I actually just started at Colorado School of Mines this August. I came from another faculty position at Wright State University in Ohio. And one of the projects that I came into is one that had started briefly before I came here, but I'm really excited to be a part of, where we're working with the Army Ground Vehicles group, so tanks, to look at sustainment applications of additive and how we qualify those components. And so what's really exciting about this project to me is I'm working with a lot of different people at Mines. We have a fairly significant team. where we're looking at data-driven qualification. So that means that we're looking at the process monitoring data that's coming off of the machine. We're looking at the powder characteristics that's going in. We're characterizing the microstructure, the defects, trying to understand the tensile properties, the fatigue properties, and all of this from a data perspective. So it brings in computer science and machine learning. And what I love about it is the breadth and being able to work with a lot of different areas of expertise. So my background is mostly additive, a lot from the processing parameters side, looking at connecting to things like fatigue performance, the effective defects. I've done mostly aerospace in my background, so I've done a lot of nickel and titanium, not a lot of steel, which is what we're working with now. But I have a ton of steel metallurgist experts that I can talk to, and they're teaching me a lot of things about what is important in steel. There's solidification experts that we're working with. There's the machine learning people, a group in physics that's developing some new sensor technologies. So I think what this really leads to is in additive, it's so interdisciplinary. The more that we can communicate and work together in teams where we have all of the complementary skill sets, then we can really tackle these big problems. Because it's so much that goes into additive. Understanding, the laser physics. I'm a mechanical engineer by trade. I've learned some over the years just by working with other people. But the more that we can build these really great teams and communicate with each other, then I think we're really going to be able to make some strong advancements in understanding all of the complexities that go into processing structure, properties, performance for additive.
Thank you so much, Joy, and really hats off to the organizers for putting together a very diverse panel, because I'm really interested to hear your opinions from advanced characterization techniques on Sarah's end, on the metallurgy side from Dana, and really Joy focusing on process optimization by leveraging simulation data sets, data science, and looking at characterization data as well. So I think it's kind of a really comprehensive spectrum of competencies that we've captured, including the academic perspectives and industry perspectives. So I'm also, my background is in mechatronics engineering, so I make very good friends with material scientists. So I really emphasize, I can't emphasize enough how excited I am about this panel. And I got super excited and came up with lots and lots of questions, but I really hope the audience members are also inspired to place questions in the Q&A as well. So I really wanted to start with the questions along the thread of, when we think of the future for metal 3D printing and powder bed fusion in particular, it's really important to understand the technological challenges that we face today. And my first question is for Sarah, but feel free to jump in, everyone on the line. What can advanced characterization techniques tell us about the process? So what have you seen in terms of leveraging all of these advanced techniques, and how can those inform kind of the future of AM and the direction of AM, specifically in powder bed fusion?
Yeah, so the characterization techniques that I use, they're always during the process. They're real-time monitoring. And this is kind of where a lot of the research on additive manufacturing is going. And it's not just, taking a look at the surface, but also probing through the entire melt pour, probing through the entire bed. So with synchrotron, with a high energy field, but if you're going for an X-ray scan, you can actually see through everything. So some of the things that you can see with the high energy X-ray is that you can actually see the melt pool and then the surrounding solid, as well as any kind of vapor phases. And this is looking through the whole material. And then not only imaging, but you can use something like the fraction, so you can see the changes in the crystal behavior as your metal melts or solidifies. And the thing with so not only can you see these changes in phases and changes in microstructure or the material, But you can also see things like pores form in real time, or any types of solidification cracking, any types of defects that you might be worried about. You can see how these are formed in real time and understand why this might form in real time, kind of like maybe there's like an unstable melt pool in your build, and because of this instability, you create a pore. The thing with advanced characterization, though, I'm glad that you mentioned diversity of the panel, because it doesn't really, it's not really useful information by itself. You need really advanced modeling techniques to actually like make sense of the physics that's happening. You need really good material science and characterization after the fact to actually look at the microstructure, because we are just looking at a 2D type of image. And you need also advanced mechatronics to actually control the process and build a certain system to actually see this. And another thing about using a high energy X-ray is that high energy X-rays are not really accessible type of facilities. So one of the things that we've been trying to do is synchronize this high energy X-ray with something that is a lot more accessible, like a CCD camera or a thermal camera. So that we can synchronize these signals and then understand that, okay, if there's a pore forming from our images in the X-ray, we see actually these fluctuations in our thermal camera or CCD camera. And then, we can take that information and actually use it in other machines that have cameras or real-time monitoring techniques. And this is also where a lot of those data-driven approaches that Joy mentioned can come in, because we're collecting a lot of data, and sometimes it's pretty tedious to go through all the images, go through all the real-time monitoring data. So you need something that like Joy has been working on to actually make sense of all that. But yeah.
Yeah, I do agree that sometimes it's very difficult to find the ground truth without extensive either manual annotation of, is this a pore, and how does this relate with what the thermal camera sees, and how do you do data fusion at large scale? So if you actually have a camera that's almost pre-calibrated in terms of what it sees using a synchrotron technique, I think that's definitely a really interesting future direction. Again, the question wasn't necessarily just for Dana and for Sarah, so feel free to jump in if you've worked on some really cool characterization techniques that you think are worthwhile mentioning. But I do think that, sorry, Joy, did you want to mention something?
Yeah, well, I was going to say, I love that Sarah mentioned the, I guess, more lab scale and the advanced characterization techniques and how they complement one another. Because I think that's something really critical in research, is being able to make that connection to an implementable technology. And so in the commercial systems, we have different types of sensors that are not going to give us all of the data that we want. They still give us a ton of data. We still have that big data problem. But being able to connect the lab scale sensors to still the fundamental science, I think is really critical. And so, I think that's great work that Sarah's doing.
Excellent. So I think in terms of advanced characterization techniques, I can see how there is promise in terms of translating those to almost commercial scale applications. In terms of the next generation or the opportunities in terms of the metals domain, I was curious to know where do you think the opportunities lie specifically for materials for laser powder bed fusion? And this is for an open question. Maybe we'll start with Dana.
Sure. So, I mean, there's a lot of different avenues that you can think about when you're talking about materials for AAM, because there's, I think everyone who's met a materials scientist knows we like the words, it depends. We always say that, but it depends on what application that you're going for, as to which avenue might be best to explore. And so I have two ways. So there's materials that are being developed specifically for additive manufacturing. And then there are materials that are being adopted because they've been made robust by other techniques, and their alloys are considered what we want in terms of their materials properties. So there's merit in both ways. But one problem that I see that's kind of the same for both of them is some of them have some pretty exotic additives to them, some pretty exotic components. And I see And this is kind of it's maybe highlighted in everybody's minds with like how we're actually experiencing some consumer shortages. We have to think of all of our resources as something that it could be potentially finite. And this is certainly the case for a lot of our alloying elements that go into metals, and especially more experimental metals that have, you know, a little itty bitty amount of one element that's only found in 2 places on Earth. Like this is something that is going to be something that we need to think about, because we either need to find other resources for that, find other sources for that element, or we need to find other elements that are more abundant, but ways that we can kind of get the best of both worlds by using abundant, but maybe less optimal additive. So I think that there's a lot to be said for materials going forward about figuring out the commercial side of things balanced with the experimental, because there's just so much, like, I'm a metallurgist, like exciting things happen when like you just start throwing things together and you just want to see what happens and see what properties you get. And then also from my mechanical engineering compadres, we always, you know, want the best performance. And I think we're going to have to compromise a lot and figure out where's that sweet spot to balance. I mean, this is great for this conference because it comes together with the economics and the technology and the people. Like there's a balance for all of these things going forward to keep this technology advancing, because it could be very difficult when we start having problems getting the alloying elements that we need. So that's my little bit. I'll turn it over to the other two. What are your perspectives?
Yeah, I think material development, if anybody saw the hot or not presentation earlier this week, it was a very hot topic voted in that presentation. I think pushing towards where we really need materials developed, a lot of high temperature applications, there's a lot in the refractory areas, which may require some machine development also to be able to get to the conditions that are needed. And I'll stretch the materials definition a little bit to feedstock forms also. Cost is a big hindrance, feedstock cost. So if we can use materials that are maybe manufactured in a less expensive way, but right now aren't processable very easily, then that could be a definite driver in materials development space.
And Sarah, I wanted to ask you in terms of looking at material adoption for powder bed fusion processes. I know essentially looking at characterization, advanced characterization techniques from that perspective, you did mention that looking at the relationship between laser material interaction or the laser material interaction can inform a lot of the direction in which, for instance, either the process parameters need to go into or perhaps the alloying elements. Can you comment on that as well?
So I've done a lot of this like directed energy deposition work mostly. So this is when you actually blow powder into the melt pool. And it's not as, it's such a messy process and it's not as developed as powder bed. But one of the things that I've tried to adopt in powder bed and seeing, you know, those laser interactions that DED is really good at is you mixing different elements. So you can mix different, you can make a bed of powder with different materials in there. Maybe you want to mix steel and I don't know if you want to be crazy, steel and titanium or something like that. And then see how, and you can see in the X-ray is actually whether they are melting. And if you put in something like, I like how Dana mentioned the exotic materials. If you put something like molybdenum, which is a really high melting point, and sometimes you want to incorporate that into your new alloy or new material, you see that it doesn't really melt as well as other materials. So one of the things that a lot of people have been doing with powder bed fusion of these dissimilar materials is just remelting, like doing constant melting passes. but you have to be careful because you might actually start vaporizing something else like a titanium or steel. So, and another thing that you see if you want to do multi-material type of builds is that like they flow differently in a molten pool. But I do think that's where laser powder bed fusion can really grow too. It's in that multi-material aspect where maybe some parts of a layer are of a different material, or the new layer that you recoat is of a different material than the layer underneath. And so, yeah, kind of understanding how things melt differently, or like where they flow, and then some materials also just want to kind of like spatter everywhere. So it's kind of understanding how each material behaves differently.
And certainly in terms of new material development, there's quite a lot of room there. And specifically now looking back at some of the work that Dana is doing with characterization of powders, I had a question for you, Dana, in terms of perhaps what are some of the areas where you can see powder characterization will kind of influence how we utilize powders in the powder bed fusion process, and potential opportunities for improvement along those lines?
So to go off of what Joy was saying a little bit ago, we have different manufacturing techniques for feedstock that result in inherently different particles. So they process differently. So I think being able to characterize that, and in a lot of ways quantifying that, because right now a lot of the morphology stuff, it does have some quantifiable aspects to it, but sometimes comparing those can be a little bit difficult, and especially in the industry space. So in academia, you have a little bit more access to, computing, to modeling, to, students that are doing a lot of coding and able to make kind of ad hoc software solutions. In industry, I think that there's a lot of room for looking at how powder spreads. This has been the watchword ever since like the first powder was spread, is everyone wants to know, well, what's the best spreading? And there's so many variables that go into it. So like everybody wants that. Everybody wants to know what's spreadability, how do you determine what spreads best. Believe me, we all want that same thing, but I think there's a lot that goes into it. And so I think that there's a lot of space. So there's rheometers that are coming out that can test the reaction to stresses in the powder bed. So that's going to be a component. Then we also have airflow or gas flow in material in the process chamber that can also have things stay packed. And then you have just packing behavior in general. So a lot of what I did during grad school was actually look at the other industries that have a lot of bulk powders or bulk materials together, and they it's like with any group, like individuals on their own, like they're approachable. You can, oh, hey, that particle, yes, that's round, that's that's very elongated. But you get them in a group and you're like, well, they behave so differently, and sometimes like we've been, so it's going to be a combination. So I feel like there's room for some drastic innovation. So inventors, get your thinking caps on and start talking with friends from other disciplines, because this is a multidisciplinary problem. And so we need to look at the shear stresses. We need to look at the packing behavior. We need to look at the behavior with gases. We need to look at like how in for example. So like DED is a totally different thing. The properties we want in powder for DED versus the powder properties we want for laser powder bed fusion, like that's going to be totally different. So like, do we come up with tests for each? And I think honestly, probably yes, because like additive, we gave it this big name, but there's so many subcomponents of additive that expecting one test to just do all of it is super high expectation. I don't know if we're there yet. I certainly don't have the answers now. I know that Joy and Sarah are both working on those answers, but I think that there's a lot of room for quantification of individual particle behavior and then bulk behavior. And there's some really cool instruments that are being developed that actually simulate spreading. Those are kind of cool. I think those are going to be interesting in how they adopt they universal? Like if you have a concept laser machine versus having an EOS M290, like is that going to be an issue, or that's going to be a lot of communication between both industry and the academic investigators. So long-winded answer. I'm sorry, I can't help it. There's just so much that goes on. Like all of these things that there's just so much. It's like particles just flying around. So many things exciting. So please, Joy and Sarah, what are your thoughts on this topic?
Not all at once. Yeah, so I think what Dana mentioned in terms of opportunities for improving properties of the powder, specifically as they pertain to the process itself, and even to the technology itself, even among powder bed fusion processes. Is it really reasonable to apply the same rules in terms of powder flow for an electron beam process versus a powder bed fusion process? Again, these are all aspects that I think would bring significant improvements to the performance of the process and the performance of the powders as they go through those processes. But related to that, I think that inspired a bit of an interesting question in the audience in terms of how do we look at powders that are being reused in the process, and how do we assess recyclability of powders once they've reached, are there any methodologies to address recyclability of powders once they have reached the end of life? So I think, have you looked at this in your work on kind of for the panelists?
Yeah, I think powder recyclability, it goes back to the feedstock is already expensive. We want to use it as long as so even understanding when end of life is, I think is still an open question. There's been a lot of research in this space, but you'll even find papers that are contradictory to one another about what results are showing up when, how do we track reusability? Is it reuse? Is it how much soot was generated during the process? How do we track those things? I have heard of some innovative approaches that are looking at when you consider your powder end of life, being able to potentially reprocess it in some way and get it back to an original or near original feedstock. I think the more that people like Dana can do research into what we actually have to characterize in our powder and what's important, that'll drive those types of technologies. Once we know what's important, we can know how to improve on it.
I've also seen some pretty promising work where they didn't use plasma atomized powders either. It was like ball milled or like hydrogenated types of powders, and it worked reasonably well, depending on what kind of qualifications you're looking for, or like what your standards are. But I will say, like, sometimes if you want like absolutely zero porosity or something, sometimes if you use recycled powder, you something like oxides on the surfaces of your powders, and also even something like porosity inside powder feedstock that remain in the built part. And sometimes these pores inside the powders, or these oxides that are present from recycled powders, are difficult to remove, even with heat treatment or some kind of post-processing. But I think it's one of those things that Dana mentioned. Like, it depends. You can get pretty good parts with recycled powders that I've seen, but at the same time, it really depends on what your qualifications and standards are.
Lots of opportunities in terms of the kind of future of powder bed fusion that pertains to materials and material recycling, which I think is something that was quite popular in the Q&A chat as well. So I just wanted to probe your ideas and outlook in terms of what do you think, what are the opportunities in terms of the next generation of powder bed fusion technologies, and where do you think that this suite of technologies is headed? And this is an open question. We'll maybe start with Sarah.
was a talk earlier from my former lab mate about hybrid processing. So right now, hybrid gives you the idea that you have to like do some machining after the post-processing, which I think it's like pretty standard that you have to do something after you build a metal AM part. But hybrid could also mean you're just adding another type of process during the build. So something that I've been really interested in is like adding electromagnetic field. So yeah, of course, this is something I just play. It sounds like I just play around in the lab, but there's a lot of like heavy like physical understanding work going into this. But sometimes what you can do with an additional external force or even in just additional type of processing is that you can modify your melt pool and you can actually change how your grains grow. You can actually dissipate porosity or something. So you can use an electromagnetic field. And this has been used in casting conventionally, where they would use an electromagnetic field during a cast, and then kind of use the fluctuating melt pool flow to actually get rid of pores or create finer grains. And it's a way more effective in metal AM because you have such a small melt pool that it's that the scalability where you can make a much bigger impact. So some hybrid processing and something that's implemented in maybe in like one machine where everything already happens. And yeah, again, the integration of all the different disciplines like data science and modeling as well.
Thank you so much. I don't know if you have any other opinions, Joy and Dana.
Yeah, I think we talked a little bit about potential multi-material powder bed earlier. I think there's desire in that area because we could do fine features with spatially controlled properties. There are definitely still some challenges. I was fortunate to work with a company, Open Additive, that developed some prototype capability to do that. One of the big things is powder recycling, though, to go back to the last category. Now we have some weird conglomeration of whatever multi-materials we used in our powder bed. So there are still some barriers to overcome there, but I think there's potential in that area. And then I think there's really still a lot to do with machine development and what we consider to be standard powder bed fusion right now. I think there's some just historical approaches that could be advanced upon. I think that work in recoding to change spreadability. You look at the vendors that are out there now, and there's different recoding technology in nearly every machine. And getting a better understanding of what is good, I think will come out. And even just improving the stability of the systems and the accuracy and making sure we have really high quality parts. I think that's still an area that will continue in normal powder bed fusion machines that we have now.
Thank you. And Dana, do you have any thoughts on this thread?
Yeah. So I think that those are all definitely areas that will definitely see a lot of growth. And we had an intern for the last, she just did a study on recoder effects on mechanical properties. So machine for, well, kind of obvious purposes, she was our intern, but so that was something that was really interesting. And I think that like broad scale comparison of that kind of thing is definitely, you know, it has effects. And there was actually just right before this, a young woman who was looking at the effects on support structures. And the recoder actually still affects things that, but they're super important. They hold it all together, the support structures. Like the recoder has an effect on that. So I think that those are definitely legitimate. What I see kind of coming down kind of the pipeline of what, you know, a lot of the companies might be thinking is, well, we're seeing like companies release with more laser power and, you know, different recoder designs, larger chambers, smaller chambers, like all of those things are also being played around with. So I think that in the industry space, a lot of it is really focused on production. So there's one thing, like in the laboratory, like these research topics get needled at and get kind of But ultimately, we want them to be headed is where we have this global digital manufacturing site where a file from one place can send my file to both Sarah, and we'll get the same part printed. Like that's I think where everybody is headed in the long run. So I think production is for a lot of additive machines, especially in development there.
Thank you. I think we're right on time, almost exhausting our time, but I just wanted to extend a really big thank you to our panelists and our audience members for all of your questions, as well as answering questions so graciously, and to Amy and the team for inviting us today to this session and putting together a really wonderful event. Thank you so much.
Thank you, ladies, and thank you, Mihaela, for organizing. You did an excellent job.